So David Nealon provides beautiful, simple ways of looking at the various feedbacks and energy balance, which of course translates to climate sensitivity. So we looked at this in the last podcast, where we said we are taking the short wave coming in, how much is reflected, how much is absorbed in the atmosphere, what makes it to the surface, and what happens when the greenhouse effect of the one layer atmosphere increases, and how the atmosphere has to adjust, and how that results in a warmer surface temperature. So this leads us to the concept of climate feedback, right? So you have increased greenhouse gases, which leads to a series of processes where both the surface and the atmosphere can end up being warmer depending on what happens with the distribution of shortwave and longwave energy. That's essentially the amplification of the warming or damping based on changes in properties like greenhouse gas concentrations. And then you can add to that water vapor feedback, as I mentioned in passing last time, ice albedo feedback, cloud feedback, and so on. So first, let's look at the radiative forcing that is caused by human activities since 1750, which is what we are talking about when we say we are changing the top of the atmosphere energy balance. These are estimated by various methods using models and observed temperatures and so on and so forth, observed concentrations of greenhouse gases, and what we know about their properties in terms of their ability to absorb outgoing long wave, and what it means in terms of the temperatures, etc. Right? So it's not a very easy thing to do. Often you depend on satellites, which have a very short time series. So when you go back to 1750, you're relying on various other methods. So human activities have produced long-lived greenhouse gases and short-lived, long-lived and short-lived greenhouse gases, aerosols, and land use. So here we have carbon dioxide, methane, halogenated gases, and nitrous oxide. Clearly CO2 dominates, and it has a positive radiative forcing, which means it has added to the energy that's being trapped, which is obvious. Then radiative forcing due to methane is also positive, but smaller than carbon dioxide. When we worry about impacts of greenhouse gases on radiative balance and warming, obviously we have to think about their concentration, their residence time in the atmosphere, how long they last, and their global warming potential, which is a relative measure with respect to CO2, often done at molecular level or per kg, in terms of their impact over something like 100 years. Okay, so look at the difference of CO2 forcing over 100 years, same concentration or same mass of methane over 100 years, and so on. So it's a relative measure. And halogenated gases, negative radiative forcing is because some of these gases destroy ozone. So that's something we have to worry about. When you decrease the ozone in the stratosphere, you are going to increase the OLR loss out of the stratosphere and cool the stratosphere by not absorbing as much UV, for example. So there are positive, net positive, but there is some negative as well in terms of the uncertainty. You can see that's fairly large. So nitrous oxide, again, lasts for a long time, has a greenhouse warming potential of, I think, almost 200 times CO2, but because it's in parts per billion, like methane, unlike carbon dioxide, which is in parts per million by volume, its net radiative forcing has been small so far, but it's a deadly greenhouse gas. Short-lived gases that create ozone or create or destroy other greenhouse gases provide multiple feedbacks. So you have several of them, all positive. Some produce large negatives here. You can look at the details in this reference here from EPA. Aerosols, again, large uncertainty remained. Black carbon can be absorbing and warming, whereas a lot of them, like sulfate aerosols, are scattering. And clouds, changes in clouds due to aerosols are called indirect effects of aerosols. So this is direct effect of absorbing or scattering solar radiation, whereas this is changing cloud properties, droplet sizes, cloud optical properties, and so on. There is also change in albedo due to land use, which is a net cooling as far as we know, reflectiveness of the Earth's surface, and change in energy from the sun in terms of natural variability over the same period is tiny, so it's not a big player. The net due to human activities then is a solid positive number. This is from 2019, so that's at around 2.5 watts per meter squared with some uncertainty around it. So this is what we have to worry about. Which brings us back to climate sensitivity. So surface temperature here as a function of emissivity or absorptivity of one layer global average energy balance model we have been looking at, which can also be converted into a amplification factor G, so it's also the top of the atmosphere greenhouse radiative forcing in watts per meter squared, not the amplification factor, sorry. Okay, so temperature delta Ts resulting from the radiative forcing is shown here, so you can see how Ts changes and infer delta Ts there for a given change in absorptivity of the one layer atmosphere we are estimating, and look at how much greenhouse gas, how much radiative forcing results from that change in epsilon A, which is basically resulting from greenhouse gases in our simple approximation. So you can fit a linear approximation to that as well, and the full solution of the one layer model that we've been using, where epsilon A is a parameter. So we can take that and write the radiative forcing G as delta epsilon A times sigma Ts to the fourth. So the outgoing long wave or infrared escaping to space emitted from the surface minus delta epsilon A sigma Ta to the fourth, which is emitted from the atmosphere itself. So the energy balance we looked at determines Ts and Ta, and we can write this as alpha delta Ts equal to G. So given a radiative forcing which is created by this process, how much amplification of the surface warming happens? So that amplification factor can be split into temperature feedback or vapor feedback, ice albedo feedback, and cloud feedback. We've looked at this before. So the net alpha then can be written as change in the atmospheric outgoing long wave radiation to space as a function of surface temperature warming minus how the radiation loss from the surface itself depends on surface temperature. Okay, so obviously 1 over alpha is our climate sensitivity that we have talked about before. And just to kind of bring us back to the models and other assessed range of equilibrium climate sensitivity and transient climate response. Equilibrium climate sensitivity, if you remember, is where we double the CO2 at some rate and hold it constant and keep integrating the model till it reaches equilibrium. And transient climate response is the temperature the system reaches when the doubling has been accomplished. So obviously committed warming means the warming will continue even after emissions have flattened out at double CO2 because of the feedbacks within the system. So equilibrium climate sensitivity using the Gregory method, which we won't go into, and transient climate response. So what the model estimates say from various scenarios, but first what was estimated by the Charney report back in 1979 using idealized model. And you can see that the range basically remains almost the same with some uncertainties. So we have improved our understanding, our model capabilities, scenario projections and so on, but the uncertainty of the climate sensitivity remains, but we are much more aware of where those uncertainties come from, like aerosols, cloud properties, and so on and so forth. Okay, so assessment report 1, the assessed range of ECS. Assessed range is basically taking multiple evidences and combining them, and experts provide an estimate as opposed to directly deriving from models. So there is the model range there. The model range for TCR in assessment report 1 is given just as a dot without a range here. And here again you have for AR2 CMIP1, AR3 CMIP2, AR4 CMIP3, and AR5 CMIP5, and CMIP6, which is being released right now. So you can see that the model range of ECS in fact here is much larger than the previous estimates and reports, and modeled TCR is come down in its range, but the value remains approximately the same at about over 2 degrees centigrade after doubling. Okay, so this is a very hairy problem. It's very complicated to estimate, and yet it's a very important problem because we are doubling CO2, we are increasing greenhouse gases, changing all the other things like albedo, aerosols, clouds, and so on. So we need to know what the climate sensitivity is so that we can know how much warming we are going to reach within the next few decades to the next century, and how long this will continue, and so on. So while very important, the difficulties remain in terms of estimating equilibrium climate sensitivity. So we'll come back and add a few more feedbacks to our energy balance after greenhouse gas perturbation to see how the warming is amplified and how that results in climate sensitivity being higher or lower. Okay, so let's do that in the next podcast.